Hello, this is the section 2.4 lesson. In this section we're going to be looking at different types of statistical graphs. Now in this section we're not going to focus on how to construct graphs. Instead we're going to focus on interpreting graphs and distinguishing between good graphs and bad graphs. So first I want to begin with a quote from the book. A graph is not in itself an end result. It is a tool for describing, exploring, and comparing data. So we don't want to construct a graph just for the sake of constructing a graph. We want to construct a graph for the purpose of better understanding the data. And so the first type of graph we're going to talk about is one that we've already seen. That's the histogram. And now different types of graphs are appropriate for different types of data. And a histogram is only appropriate for quantitative data. That comes in it's data that comes in the form of numbers. And so last section we constructed a histogram of the body temperatures. Those body temperatures were numbers, and so that's quantitative data. One thing we use the histogram for is to see the quote-unquote shape of the data. We look for a bell curve shape or possibly some other type of shape. We also use a histogram to answer questions like, are most temperatures near 98.6? We see from the histogram that bin or that category containing 98.6 is the most frequent. But we had some that were quite a bit less than 98.6 and some that were quite a bit more. We can also use it to answer questions like, is the data normally distributed? Does it have a bell curve shape? In this case it kind of does have a bell curve shape, so that's an indication that the data is normally distributed. Second type is one that we're all familiar with, and that's the pie chart. So let's suppose that we go out and we ask of 300 students, do you like the food in Janzhou cafeteria? And 56 of them say yes, and 244 of them say no. Now obviously a lot more people said no than yes, and we'd like to illustrate that point. Well, the numbers illustrate that well, but numbers are kind of hard to look at. Most people don't like looking at numbers, they'd rather look at pictures. And so a pie chart gives us a way of illustrating that many more than half said no. And of course we all know what a pie chart looks like. Something kind of like this, or we got a circle, we got one slice for the yeses, one slice for the no's. And the yes slice is a lot smaller than the no slice, and that illustrates our point that we want to make. Now one important thing to remember about a pie chart is that it's used for qualitative data. That's data that does not come in numbers. In this case the data that we collect is a list of yes and no's. Those numbers of 56 and 244 are not the data. Those numbers simply summarize the data. And a pie chart illustrates how much of each category contributed to the whole. So we have two categories of answers, yes and no. There's 300 of them total. We see that no contributed a lot more to the whole than did the yes. So that's a good use of pie charts. The next type of graph is one that we're probably not very familiar with, and that's called a Pareto chart. And so to illustrate this, let's suppose that the operators at a phone company record what type of complaints people call in with. And here we have 7 different categories of complaints: rates and services, marketing, international calling, so on and so forth. And so that first number says that 4,473 people complained about rates and services. 1,007 complained about marketing, so on and so forth. So we've got these 7 different categories of complaints. Now note that our data are qualitative here. Our data are lists of complaints. Those numbers in the right-hand column are not the data. Those numbers simply summarize the data. So what we'd like to do is illustrate how these categories compare to each other. Well, just looking at the numbers, we see that the most frequent complaint was slamming, the second most frequent was rates and services, the third was marketing, etc. But again, numbers are hard to look at. We like to draw a picture of what those numbers are telling us. Now we do have qualitative data, so we could use a pie chart, and here's what the pie chart for this particular data would look like. Notice it's kind of messy. It's kind of hard to read with all those labels and numbers, and if we just tried to compare categories by looking at slices, it's kind of hard to tell which slice is bigger, which slice is smaller, especially when we're looking at some of those smaller slices. So a pie chart is appropriate, but it's not the best choice. And in fact the author and most statisticians say to avoid pie charts altogether. A little bit later in this lesson we'll talk more about why we want to avoid pie charts. So a pie chart is appropriate, but it's not the best choice. So instead we're going to construct what we call a Pareto chart. And a Pareto chart you may also call a bar graph or a bar chart. And so what we have here is one vertical bar for each category. We'll put the most frequent category on the left, the least frequent on the right. Now at first glance this is a little complicated to read. This Pareto chart was generated by the program called Minitab. And it gives kind of a somewhat complicated Pareto chart. Other programs give simpler Pareto charts. But what's really important here are these vertical bars. We have two vertical axes here. One is count or frequency and the other is percent. So for instance we see that slamming had a count of about 12,500, and that was about 60%. Rates and services had a frequency of just under 5,000, and that was a little over 20%. And so we can see right away just by looking at the picture that slamming is the most frequent, rates and services was the next most frequent, but it was quite a bit less than slamming. Cramming was a little bit less than half of rates and services. Marketing was pretty close to cramming, and so on and so forth. And so just looking at the bars there, we see which one is most frequent. We can very easily compare different categories. Now that red line on top, it graphs cumulative frequency or cumulative percent. We don't need to worry about that. What's important there are those vertical bars. One important point here is that a Pareto chart is again used for qualitative data like a pie chart. And a Pareto chart is good for comparing multiple categories. If I've got 7 categories or more like we have in this case, a Pareto chart is going to be a much better option than a pie chart. Next type is another one that you're probably familiar with from high school algebra. That's what we call a scatter plot. And high school algebra, you plotted x, y points on a coordinate grid. And well, that's basically the idea behind a scatter plot. What we have here is some data that gives the weights of some different cars and their corresponding highway miles per gallon. So we see that the first car weighed 2,290 pounds and has 37 highway miles per gallon. The second car is 2,440 pounds and it has 37 miles per gallon, so on and so forth. And so what we want to look for is a relationship between the weight of a car and its miles per gallon. What we probably suspect is that the heavier a car is, the lower its highway miles per gallon. Now if we look at the data, specifically at the weight column, notice as we go down the table the weights increase, and at the same time we go down the table the miles per gallon decrease. So that kind of confirms our suspicion. But again, numbers are hard to look at. I don't like to look at a big table of numbers like this. I want to look at a picture of those numbers. Okay, and so the scatter plot is graphed here on the right. We have our two axes, a vertical and a horizontal axis. On the horizontal axis we have weight, and the vertical axis we have miles per gallon. And so to graph that first pair of data, we go over to 2,290 on the vertical axis, or excuse me, on the horizontal axis, and then we go up to 37 on the vertical axis, and we put a dot there. And then the next one we go over to 2,240 and up to 37, and we put a dot there. We just do that for each pair of data. And so in the scatter plot we see that as we move from left to right, the weight increases, at the same time the miles per gallon decrease. And in fact we can see that those dots kind of form almost a straight line that slopes down from left to right. We're going to use that observation in chapter 10. Now a scatter plot is only appropriate for quantitative data that come in pairs. In order to make this type of graph you have to have numbers, and they have to come in pairs. You have to have, well, for each car we have one weight and 1 miles per gallon. And so anytime we have quantitative data that comes in pairs, a scatter plot is going to be an appropriate type of graph. Our next type of graph is a variation of the scatter plot that we just saw. This is what we call a time series graph. And so here we have some more quantitative data that comes in pairs. And what we have here is is data on the number of runway near misses for different years. A runway near miss is where two airplanes almost run into each other on the runway. So we see that in year 1990 there were 281 near misses, in 91 there were 242 near misses, so on and so forth. And what we want to look for is a trend. Is the number of near misses increasing? Is it decreasing? Is it fluctuating up and down? What's going on there? Well, if we just look at the numbers, we go down the list, we see that year increases, and at first the near misses starts to decrease. It goes down to 186, and then it starts to increase, and it makes a slight dip there between 98 and 99, but then it spikes there at the end. So we see there's kind of fluctuating a little bit. And again, numbers are hard to look at. I want to draw a picture of this. So this is we have quantitative data that come in pairs. So a scatter plot is appropriate, but we're going to do a slight variation of this. And so we're going to plot each pair of data pretty similar to what we did with the scatter plot, but the difference here is that we're going to connect each dot with a straight line. And so from there we can look at the picture very easily and see go from left to right. The number decreases, starts to increase, it makes a slight decrease, and then a sharp spike there at the end. So that shows the trend. So again, this is just a variation of a scatter plot called a time series graph. And what makes a time series graph is that the horizontal axis is time. In this case, it's time measured in years. It could be any units, it doesn't matter, but horizontal axis has to be time for it to be a time series graph. Now, those are only a few of the types of graphs that people can use. In the book they talk about more, in the homework you'll see a few more. But let's talk real quickly about some bad graphs and then some good graphs. A lot of different types of graphs we can use. Some are better than others, and sometimes graphs are maybe a little bit misleading. Here's an example of that. Here's a graph that compares the median weekly income for men and women. And so if we just look at the picture without looking at the numbers, it looks like men make more than twice as much as women. But then if we look a little more closely at the numbers, we see that men make 377, whereas women make 331. So men do indeed make more according to this data, but the difference is not quite as great as originally thought. So this is a little bit misleading. The problem here is that we have a bad scale. If you look at the vertical axis, we see that it starts at 300 rather than 0. A better way to have drawn this would be to start the scale at 0. And so there you have the bar for men and one for women. Again, the men's is a little bit taller, but it's not as disproportionately taller as it is in that first one. Now here's a good graph, an example of one that you might see in the magazine Consumer Reports. This graph compares two different kinds of cars, the Firebrand and the Speedster, in terms of different categories, the engines, transmissions, electrical, so on and so forth. And then we also compare different model years. And you see the key there, a solid green means good, solid red means bad, and then those ones in between mean somewhere in between good and bad. And so we can see, for instance, that for the Firebrand, in terms of driving comfort, it starts off as not very good, and then it increases in quality. To 06, it's very good. And if you look at like safety features for the Speedster, we see that it's bad in every year. So this type of graph may be a little bit confusing the first time you see it, but there's a lot of information packed into a small space, and that's a characteristic of a good graph. Okay. Here's another graph that some people claim is the greatest statistical graph ever created in all of history. This one's very confusing the first time you see it, but it's very ingenious. It packs a lot of information into a small space. The title here is Loss into Soldiers in Napoleon's Army During the Russian Campaign, 1812 to 1813. And if you know anything about history, you know that Napoleon tried to conquer Russia in the winter of 1812 to 1813, and basically it was a disaster. He lost basically his entire army. So this graph illustrates the kind of the direction that the army marched, the distance they marched, and the size of the army. So if you start there at the left, it says army begins here with 422,000 men. And that green or blue band illustrates the size of the army. The width illustrates the size, and also shows how they march. So if you see they marched from left to right, notice that the band is getting smaller, and it illustrates that men are dying because of disease or starvation or battle or whatever. So when they get to Moscow there at the right, they have only 100,000 men left. When they reached Moscow, they discovered that the city was deserted, and so they turned around and started marching back, and that's the red band. And so you can see going from right to left, you see how the band gets narrower and narrower, and by the time they get back to where they started, they only had 10,000 men left. You also see a scale of miles. Down at the bottom, you see a scale of temperature below freezing. That's on the march back. So you see it started off at 32 degrees when they left, and when they finally got back, it was negative 15 degrees. So a lot of information packed into a small space. That's a characteristic of a very good graph. And so that leads to our first of our two rules for what makes a good graph a good graph. The first rule is to minimize ink to data ratio. Okay. Now what do I mean by that? Well, let's look at this pie chart of those that we saw before. Do you like the food in Janzhou? Yes or no? Now it took a lot of ink to draw this graph here, but there's not a lot of data. There's really only two pieces of data: the number that said yes and the numbers that said no. So we have a lot of ink, not very much data, so we have a high ink to data ratio. However, if we look at this graph from Consumer Reports magazine, it did take a lot of ink to draw this graph, but there's also a lot of data there. So a lot of ink, but a lot of data, so it means we have a low ratio. So that's a good graph. This illustrates why pie charts are typically bad graphs, because they have a high ink to data ratio. The second rule is based on a quote from a book, which says a sentence should contain no unnecessary words, a paragraph no unnecessary sentences, for the same reason that a drawing should contain no unnecessary parts, and a machine no unnecessary parts. And so the point here is that your graph should not contain a lot of unnecessary stuff, whether it be lines or colors or anything. So if we look at a pie chart here on the left, okay, that's just a simple pie chart. We've already illustrated the pie chart is not very good, but what some programs allow us to do is to draw fancy looking pie charts, like this one here on the right. This is kind of a three-dimensional pie chart. The same pie chart is just broken up into three pieces. So it looks fancier, but notice that it doesn't contain any more data. In fact, it contains the exact same data, but it contains a lot more lines and a lot more unnecessary stuff that distracts you from the real point there. So a pie chart is bad enough, but you do a three-dimensional pie chart, it looks fancier, but it's no more better, and in fact it's even worse. So stay away from fancy looking charts just for that you think look fancier just because they are. Alright, so that's it for this section. The homework is section 2.4 on Course Compass, and I'd also like you to read section 2.5 from the ebook. Section 2.5 will talk a little bit more about the difference between good graphs and bad graphs, and the homework will contain some problems from that section.